to record, ignore like that double thing, and I apologize. All right, so now we need to do the same thing, but we need to do the same thing for the gravitational force from the bear or the ladder. That has components. And the gravitational force from the bear has components. Because again, we need the piece that's perpendicular to the ladder. Okay? So now comes the tricky part. Is figuring out where the angle is for the two gravitational forces. Okay? So I'm going to do this on a separate picture. All right, so we already had this one. We had its vertical and horizontal components. We had the angle was here, and the angle was here, and the angle was down here. All right, now we have our gravitational, let me do the gravitational force of the bear. Gravitational force from the bear, gravitational force from the ladder. Okay? All right, so we said this has a vertical component here, and this has a vertical component here. All right, so we're trying to figure out where the angle is. So in my mind, this is how I look at it. These also have x components. So those x components are parallel here, okay? Well, these y components are parallel to this normal force. So since these are parallel, that's my 50 degrees there. How did I do this earlier? All right, so we got a bunch of parallel lines here, all right? That's a 50, this is a 40, because that's perpendicular there. That makes this a 40, okay? So this 40-degree angle here corresponds to these 40-degree angles there. You can also think of those 40-degree angles being here, which means my 50 has to be here now. I suggest trying it out for yourselves at some point and looking at where all those angles fit in. But what that means is my components here is the gravitational force of the ladder times the cosine of the angle now. So the normal force at the top was sine of the angle. These gravitational forces are the cosine. So what I will say is if you're going to see a ladder problem in multiple choice, it's not going to have the added mass on there usually of the bear. It's just going to be a problem with like a bar like that. And they're going to ask you something about its rotation or the torque. It'll have something holding it up here at this end in some way. You're going to see an example of that in the quiz today. You're going to use the same kind of strategy, okay? So this one we said was the gravitational force of the ladder times the cosine of the angle, because theta's up here. So this side is the gravitational force of the bear with the cosine of the angle, okay? Now we have our torques, so we can do our sum of the torque equations. And we're doing that because we know this force and we know this force. We know their locations here, so we can calculate those torques. And using that information, we can find the torque from the normal force, and then therefore we can find the normal force, okay? So if this is in equilibrium, the sum of the torques equal 0, which means the sum of the clockwise torques have to equal the sum of counterclockwise torques. So the gravitational forces from the bear are going to cause rotation in that direction. The wall counters with the torque in the counterclockwise direction. So we get the gravitational force of the ladder times the cosine of the angle times its location, which is L over 2 for the ladder. We get that with the gravitational force times the bear, the cosine of the angle, times the location of the bear. I don't have it as a fraction. I have it as a number. Can't see my decimal in there very good, or my plus very good. And that has to equal the torque from the wall, which is the normal force from the wall times the sine of the angle times the length of the or the distance from the pivot, which is the bottom for this one. So what we end up with is 400 times 4, because the length over 2 is 4, times the cosine of 50 plus the 2000 times 6.3 times the cosine of 50, and that has to equal whatever that normal force is times the sine of 50 times 8, because that's the whole length of the ladder. And if you do the math, you find out that the normal force was equal to 1,489 newtons. So that's from the wall. The problem asked for two more things. It asked for, sorry for scrunching it in there. It asked for two more things. It asked for the coefficient of friction, static friction down here, and it also asked you to find the normal force from the floor. So now it just becomes a forces problem like before. So let me clear all these markings. Clear ink. All right, so now we know the normal force from the wall is equal to 1,489 newtons. Now we can figure out the frictional force, because if we go back to our original diagram here, now we have this force. What must be true about the frictional force if this is in equilibrium? They have to be equal to each other. So the sum of the forces in the x direction have to equal 0. The sum of the forces in the x direction are that normal force from the wall minus the frictional force. So the normal force from the wall have to equal the frictional force. You have to justify this in some way. This is your justification, saying that you know that it has to equal 0, your total net force. So the frictional force has to equal 1,489 newtons. They asked for the coefficient of static friction. So we have to now look at the equation for that friction. This is a static friction force. So technically it's less than or equal to, they're asking you for the minimum static coefficient of friction. So we have to use the equals. It's that times the normal force from the floor, because this is the static friction force between the ladder and the floor. So we can use sum of the forces for that. The sum of the forces in the vertical direction have to equal what if it's in equilibrium? 0. So we had 3 vertical forces. We had that normal force from the floor going up. We had the gravitational force from the ladder going down, and the gravitational force from the bear going down. So that means the normal force from the floor has to equal the gravitational force from the ladder plus the gravitational force from the bear, or the 400 plus the 2,000, which is 2,400 newtons. And now we can take that and figure out our coefficient of static friction, because the the minimum coefficient of static friction is going to be that static friction force divided by that normal force in the floor. So we can plug that into the bottom, we can plug that into the top, and we can get our coefficient of friction. So common questions from situations like these rotating bars, like a ladder or something like that, is asking for the coefficient of friction, asking for the torque provided by the gravitational force. It's just, they could be all kinds of different ones. And so I'm going to show you the different ones that they have asked in the past, either through quizzes or through problems we're going to do together in class. Okay?